All right, welcome to our exploration. It all begins here. But before we do that, let's make sure that we're on the same page when it comes to number sense. The skill required to be able to understand this concept is to be able to multiply a number by itself. All right, let's do, these are some type of numbers that we should be able to multiply by themselves. I'm gonna highlight a number, for example, 8. And hopefully you are thinking 8 times 8, 64, and get to the answer before I say it out loud. I'm gonna say all the answers out loud. So let's get started with this number here. 16, and this number. 1, and this number. 4, and this number. 100, and this number. 49, and this number. 16, this number. 16, this number. 9, this number. 9, this number. 1, this number. 1, this number. 0, and so on. Really quickly, just to emphasize these two, I don't want to escape these two. Let's try this one. I'm going to count to 3 and then say the answer out loud. 1, 2, 3. 1 over 9. And this one. 1, 2, 3. 25 over 4. So hopefully you're checking that not only did I square the numerator, the number on the numerator, but also the one on the denominator, right? So 1 over 9 was this number times this number, and this number by times itself is 25 over 4, all right? That's one that you should be familiar with. And another special case was this one, and hopefully you identified something I want to highlight next, which is the question I wrote for 1B. So therefore, my labeling will go in this format. This is 1A, if the next one is 1B. What kind of numbers did we get in return? So for example, when I highlighted a -4, a -9, a -1, did we get negative, positive, or 0 numbers in return? When we squared a negative type of number, we always got what type of number in return? A positive number. And when we square a positive like 10 or 12 or 7 and 4, what kind of number did we get in return? We got positive. Did we ever get a negative number in return? So that's what I want you to think about. What kind of numbers did we get in return? For sure, we got a positive number. So I'm gonna write the answer in green for this one right here. We got positive type of numbers for sure. We get positives. Did we ever get a negative? Is there a number that we multiplied by itself and got a negative? I think the answer is no, right? And you can think of not from thinking from these, but can you think of any other examples that are not written here where the answer is yes, we can get a negative number? We were going to say that no, that's not possible. And the one other number that I'm trying to think of is there any other type of numbers that we got? And I'm going to put negatives and say no, we don't have any negatives. All right. And then what is the number that separates the positives from the negatives? There's one number that's that boundary. It is 0. Can we get 0 as an answer in return? Not all the time, but was there a specific case that gave us 0 in return? And there it is. 0 times 0 is 0. So only two possible type of values, positives and 0. Remember, not negative. I want to emphasize we don't get any negatives in return. So that's a key question to keep in mind moving forward. All right. So, all right, let's start exploring. The way that I want to show you this is by a very familiar shape that we've seen before. And these are all squares. All right. Not all of them drawn to scale, except the first two. The first two I drew to scale. So let's start labeling those units. If you can see the grid, count with me. This is how many units? It is 2. If not, just trust it from far away, or I hope you can see that clearly. Then that means that how many units here is 2. And what it's asking about area is, think of the smaller squares, like those square tiles that looks inside. How many of those tiles would take to fill up the larger square? And you can see that it is 4, all right? 2 times 2 is 4. That's one way to do it, or counting them all rapidly. All right, and this one has a dimension of 3, so 3 units and 3 units. And therefore, how many of those little squares inside will it take up to fill up the bigger square, the larger square? That's what it means by area, if you needed that refresher. But hopefully you don't need that. I just put it there just so you can get that nice visual. So the area is I'll write it in a different color. Let's go with red. The area for this one is gonna, let's do the smaller one. The area is gonna require 4 of those little smaller squares. How many of these little squares are required for the 3x3 square? It's going to be 9, area of 9. That's what we mean by area of 9 little squares, or 9 little square units. All right, so if you heard that before, that's what it represents. Okay, so to move on, I'll just go back to the green, I guess. And the next few we just assume that are not drawn to scale. So suppose that this side length, let's start with this one right here. Suppose that the side length for this one is 8. If the side length is 8, what is the area? The area is 8 times 8, right? Or 64. Because we did 8 times 8, just like we did 3 times 3 on the last one, and 2 times 2 on the previous one. And if you know the special name for it, this is an explanation of why it's called that. All right. What's these? If the side length is 10, what is the area? The area is 100. The next one, if the side length is 6, what is the area? The area is 36. And if the side length is 7, what is the area? Area is 49. If the side length is 13, what's the area? The area is 169. And how did we get that? Let's start thinking about that. For the next one, if the side length is 12, what's the area? It is 144. How did we get that? 12 times 12, right? 12 times 12. And now there's a special name for that. If you are familiar with that, that is called, it's another way of saying 3 times 3. That's more convenient. It is 3 squared. So hopefully you have seen that before. And if not, then this is the first time we're going to get used to seeing that notation. This one is 2 squared. 2 times 2 is what we did to get that. And 3 squared was 3 times 3. So if you have heard that before, this is called 3 squared. 3 squared. And that little 2, this little 2 up here, it just means it's a 3 in 2 dimensions. It's a 3 in 2 dimensions. Notice how we have 2 dimensions of 3 making a square. If you know the cube, that's exactly what it means. You can carry that same logic forward. So therefore, this square is this is the same as an 8 squared, and we can write it as 8 squared. It's the same as 64. This next one is a 10 squared. This is a 6 squared, of course. And I put 8 for area. This is a 7 squared. It's known as a 7 squared, 7 in 2 dimensions. This is 13 in 2 dimensions. This one is 12 in 2 dimensions. And that's the idea, all right? And what I wanted to use for the last ones is always going back to the idea, if you need further challenge, you can always throw fractions into the mix. So for example, suppose that we had a side length of 4/5. And the next square has a side length of x. What are their areas? So this area would be a 4/5 squared, or 16/25. And this one right here, x times x. Remember that x times x is what we do to get the area, but now we can call this an x squared. And x squared is just a square with side length of equal length labeled as x. That's the way we can think about it. So when you think of that operation, if you ever heard that term before, I'll write it in green up here as maybe a definition we can start to introduce once we saw the concept. Squaring, this operation is squaring. If you have never heard that before, squaring is when you have like an example like 4 times 4 equals 4 squared. Or any of those below, okay? I just wrote the one that came to mind. All right, but there it is, squaring visually. Most people are used to just memorizing this fact, but they don't ever get a visual, or if they do get a visual, they only see it once and don't ever think about it. but just know that when you're squaring a number, it really represents the area. Squaring a number represents the area of a square with that given side length. So at first I introduced it as area, but then I will start referring to it as what's the square? The area of the square, pretty much, okay? And that's that idea there. Now let's work with squares right here on 2b, but let's reverse this. Let's reverse this idea. Rather than asking for what's the area, now we're gonna ask for what is the side length. But of course, if we're asking for the side length, then now the area must be given to us. So let's suppose that, let me see, let's go with green. There we go. Let's suppose that the area of this square right here is going to be 16. The area of this one is 16. What's the side length? The side length was, well, we have to think something times something was 16, and hopefully you figure out that was a 4. Good. If the area of the one on the left is 25, what was the side length? The side length was 5, right? And if the area was 64, what was the side length? The side length was 8. Great. If the side length, I'm sorry, if the area is 121, what is the side length of the square? That's right, it is 11. And if the area is 49, making sure that I didn't do that one yet, what is the side length? It is a 7. And if area is 100, what is the side length? 10. And if the area is 169 and 196, think about those. Those are easily confused and mistaken by students. This one is 13. The side length is 13, and this one is 14. If the area is 1, that's another one that might be a little confusing, but it shouldn't. If the area is 1, then the side length was also 1. All right. Excellent. So that's the main idea. And again, what I want to point out is, for example, if we have something like p squared, what was the side length? The side length was, of course, p. But that's the most common knowledge on this. Let's explain, let's think about this more. What I want to think about is, what did we do to the number to find the side length? So for example, for 16, how did we get a 4? We thought, oh, something times something, right? That has to be the same number, and that was 4. Okay, what happened to the 25 to become a 5? It was 5 times 5. How did the 49 become a 7? It is 7 times 7, and so on. That's the main idea, all right? If you understand that, great. Now, there is a name to this also. And if you think operations, some of you might know the name. Is there a name or an operation that exists that we can perform to this 49 to get a 7? Is there an operation that we can do to get a 10? An operation that we do to 196 to get a 14? And I'll give you a hint. It also has the name square on it. Just like the previous squaring, this one also has the name square associated with it. And you might have heard it. It is called the square root. And that's really what it is. If you think about another way of representing 7 is, for example, this side length in green is 7, but isn't it also the same as the square root of 49? Because what's the square root of 49? It is 7. If you are familiar with that, that's what it means. If not, this is your first introduction to it, and I'm showing it to you visually. What's another way of representing the side length of 10 here? We can say this is the same as square root of 100. What's the side length for 1? It is square root of 1. And therefore, how can we label, what's another way of labeling this side length right here? Rather than p, we can say the square root of p squared, which is the same as p. Very nice way of showing that. And equally with these, we know that 196 is the same as 14 squared, so we can say this is the square root of 14 squared. And that is just a 14. So you can see those are the same. That's a very nice visual. So what square root means, I know that most of you who have seen it or have taken algebra a long time ago have seen it as the symbol before, where you know that the square root of x is x, something like that. This is how you remember it from high school. I never really probably understood it. But all that a square root means is asking, what is the side length of the square? So that's what I wanted to say. The side length of the square is the same as the square root. The side length represents the root of the square because they have the same dimension. The side length is the root and the area is the square. The side length is the root and the area is the square. The side length is the root and the area is the square because the 100 is 10 squared. Here's the square, here's their square root. Here's the square, here's the square root. All right. So all we're going to think about when we hear or see square root in the future is just asking what's the side length of the square. That's all we need to know. So hopefully you're feeling comfortable with these two new terms, or possibly terms that you didn't quite master before. Don't worry if you haven't yet. It's going to take some time. We're going to continue to do this. All right. But I wanted to give you a nice visual for what square root means, what it looks like. So that way you don't always have to, draw the squares, but at least know what it and understand what is being interpreted by the symbols. All right. Okay. So that's very good to point out. Once again, before we move on, the area is the square and the side length is the square root. All right. So if you want to drill that into your brain, that's the way you want to think. And one of the reasons why I want to point that out is for the next part, this one I made specifically because I heard a lot of my students have this misconception, and not only students, but I watch a lot of YouTube videos that are math related, and I've even seen some instructors say this term or this phrase, which I'm gonna try to refrain from now, but show you the concept and then tell you what it is that I've seen students and instructors say and do. What I want you to think about is what was squared to obtain these four numbers. All right, what was squared to obtain a 49? Meaning like what quantity or what number, what was squared to get a 25, what was squared to get a 1, and what was squared to get a -1. Let's think about those. Give you about 10 seconds or so, maybe less. No, I don't think you need it, but let's check now. Okay, what was squared to get a 49? Most popular answer is a 7. 7, and I hear 7 often. What's the most popular answer for 25? It is 5. How about this one right here? It is 1. And we'll leave this one for the end. This one's actually its own special case, but these three are very similar. All right. So when I ask this to my students, a lot of the time they say, oh, I'm gonna write a different color. Let's go green because this is important. What was squared to get a 49? It was a 7. What was squared to get a 25? Oftentimes I hear 5. And then I ask my students, are you sure? Or the people that I'm working with, are you sure? And they say, yes, of course. And then I say, is there anything else that you can square to get a 49 or a 25? And then kind of something triggers in their brain and they go, oh, and if they don't, even if you don't see it yet, I'm gonna ask you some questions so you can get there. And maybe write them right here. Think about squaring two numbers. Now that you're familiar with what this means some number being squared and some number being squared. Let's compare 4 squared with -4 squared. What is 4 squared? It is 16. And what is -4 squared? It is also 16. So notice how you can square two different numbers to get the same value. And then hopefully you can see it. It is 7 or a -7. 7 or -7. There's two possible values that you can square to get a 49. And then how many possible values can you square to get a 25? Hopefully you can see it's 2, it's 5 and or -5, I mean. In this case, it means a 5 or a -5 or both. In the math class, that's usually what or means. And -1 or +1. Right? So hopefully you can see that. And before I go into this one, I'll tell you what I've seen a lot of my students do is like, oh, we're just taking the square root. And then they take that further to say, oh, there are 2 square roots. Okay, so please be careful with that. I've seen a lot of my students, what are the square roots of 25? They're 5 and -5. I heard some instructors say, what are the square roots of 49? And that's not correct. Remember the picture. Square root means the side length of a square. Think about that. Can the side length of a square ever be negative? If you think back to your early geometry foundation, can the side length distance ever be negative? And the answer is no. So therefore, there is only one square root. Okay, so please think about that. There is, I'll write that here in green maybe because it's important. There is only one square root. only one square root, but there are two different numbers. That's the main difference. But two numbers can be squared. So I'll write that down because it is important, and hopefully you think about it yourself. But two numbers can be squared to the area. All right, so when we say that, there's only one square root of 49, which is 7, but two different numbers can be squared to be a 49. That's what pretty much it says in writing. All right, there's only one square root to 25. A side length of a square can only be 5, not -5. However, we can square both of these separately and still get the same number. All right, same here. The side length of a square cannot be -1, but those two numbers can be squared separately and get a 1. So that's what this sentence is trying to emphasize here. All right, and hopefully you didn't miss that part of the video. If not, you can always come back and watch it later. But the next one is also very key to talk about, because now this is saying, wait a minute, if that's the way we're interpreting, that means that this one represents the area of a square, and it does, absolutely. And that this 25 represents the area of this square, and it absolutely does. And this 49 represents the area of this square. So that in that sense, it's saying that this -1 represents the area of a square. So can the area of a square ever be negative? And I don't want to answer that yet because it's a controversial answer at this point. But just think about it. Area cannot be -1. That's what that is implying. Area cannot be -1. So we will say there's no answer to that one in the real world. Let's just say that right now. Let's say no solution for this one. No solution in the real world. And that's as much as I'm going to say about that. I don't want to talk about other worlds right now. In the real world, all right? Just think about it that way. No solution in the real world. Really, it's going to be in the real number system later. But again, I'm not too big into big vocabulary and stuff like that right now. So let's just move on. I just wanted to show you that concept. And please understand that the area inside of the square cannot be a negative number. Therefore, this does not have a solution. And the other two only have one square root, but two different numbers that can be squared to get that value, that area value, okay? And then this is really the notation you're gonna see in the future. And remember that square root of 49 implies the area of the square is 49. What's the side length? The side length was 7. Oops, let me go back to my green color. The side length was 7. All right, I want you to interpret this as, what is the area of the square? It is 25. Therefore, what is the side length? It is 5. And remember, it's only 5, not plus or minus 5, positive and -5. Only 7, not 7 and -7. And if the area is 1, what is the side length? There is only one possible value. It is a 1. And this one, we say no solution. No solution. Really, what we're going to say in the future is in the real world, in the real number system. No solution in real numbers. We'll talk about those other numbers at some other point. But yeah, this is really great. If you understood most of what we did today or all of it, this is as far as I want to take you on our first little practice and exploration of squares and square roots. Hopefully you feel a lot more comfortable with them, and we're going to continue working with these forward. Stay tuned and watch the next series of videos to keep getting better or practice your own. Goodbye, guys.